All right, everyone, in this next video, we're going to discuss how to solve structure elucidation problems. Those structure elucidation problems, just to clarify, are these problems where we're given a spectrum or integration values, your molecular formula, and you have to fully deduce the identity of the unknown compound. Now, here's my personal strategy for how I go about solving this. The very first thing that I'm concerned about with is actually the molecular formula. What I'm going to do is calculate the number of IHD present, which is sometimes called the degrees of unsaturation. This calculation is super easy to do, and it will give you a sense of the number of potential pi bonds and or ring structures that are present. I'll teach you how to do that on the next page. That can often tell us if there's multiple pi bonds or a benzene ring. We'll use that to our advantage. It's the very first thing that we do is calculate the number of IHD present. After that, what we're going to do is generate an anchor point. Now, by generate an anchor point, I mean we're going to use chemical shift to our advantage. We're going to start with our most downfield signals, go our way upfield. So for example, let's say you had a 2H signal that's shifting in the 3 to 5 region and you have an oxygen in your molecular formula. We could use that as our anchor point. 2H in the 3 to 5 region would signify that there's a CH2 bonded to an oxygen. That's our anchor point. Chemical shift gives us that anchor point. That's why we need to know chemical shift really well. If we don't, then we're kind of a little bit unsure about the connectivity we should make. Now, after you get that anchor point, what we're going to do next is use the splitting pattern, and splitting pattern in combination with the integration to build out that chain. For example, let's say that your anchor point is split into a triplet. That might indicate that there's an adjacent CH2 present. Let's say that instead it's a quartet. That might indicate that there's a methyl group present. And we're going to use splitting and integration to build out that carbon chain, which we'll illustrate shortly. And sometimes we build and we get to the end of a piece. For example, we might know that there's an OCH2CH3. That's one piece of the puzzle. We might then have to build other pieces. We never want to force connectivity. We want to read connectivity. And I'll illustrate how we go about this in a little bit here. So we might build multiple pieces, and ultimately we need to combine them into a proposed structure that aligns with all of the data, right number of signals, right number of IHD, correct splitting patterns, all of that needs to align. So we calculate IHD, generate an anchor point, use splitting and integration data to build that out. We might build multiple pieces. If we complete one piece, we then go to the next most downfield signal, get an anchor point, continue to build, and then put it all together. Now, next thing that we need to do is talk about the IHD. So this is also called degrees of unsaturation. And one IHD can either indicate the presence of a ring or the presence of a pi bond. 1 degree is 1 ring or 1 pi bond. Where this is derived from is this. If you had a fully saturated compound, meaning that there's no pi bonds, no rings, it should fulfill the formula of CnH2n plus 2. Meaning if this is C5, there should be 2 times the number of carbons plus 2 hydrogens, C5H12, Cn2n plus 2 for the hydrogens. Now, if I were to have a 5-membered chain with 1 pi bond, that should now be C5H10. If I were to have a 5-membered ring only, C5H10. Notice as we introduce a ring or we introduce 1 pi bond, there's a deficiency of 2 hydrogens relative to the amount of hydrogens that we'd expect for a compound with the same number of carbons that is fully saturated. Okay, that's where we're going to derive this calculation from. 2 degrees or 2 IHD might mean 1 ring and 1 pi bond. If I had 4 degrees, or we could say 4 IHD, that could represent a benzene ring, 1 ring, 3 pi bonds. 6 IHD, 6 degrees could mean a benzene ring constituting 4 of them, and then 2 other pi bonds. Okay. Now, this is a really simple calculation. To calculate the IHD, we take the theoretical minus the actual over 2. Now, your theoretical value is going to be derived by taking the number of carbons in your molecular formula, multiplying by 2, and then adding 2. The actual value is the number of hydrogens in your molecular formula. And that actual value might need to be adjusted. That's why I've included this asterisk there. For every nitrogen or phosphorus present, you'll need to subtract 1 hydrogen from the actual value. And for every halogen present, you'll need to subtract 1 hydrogen from that actual value. For example, let's say I have C8H7N, and I wanted to do the IHD calculation. I'm going to first get my theoretical value, number of carbons times 2 plus 2, which would give me 18. That's 8 times 2 plus 2. Then for my actual value, because there's a nitrogen, I need to subtract 1. That gives me 6. 18 minus 6 would be 12. 12 over 2 is 6. Okay. Or let's say I had maybe C10, H13, Cl. IHD calculation would be number of carbons times 2 plus 2. That would give me 22. 10 times 2 plus 2. Then in terms of my actual number, I've got 13, but I do have 1 halogen, so I need to add 1 to that actual value. That would give me an adjusted value of 14. 22 minus 14 is 8. 8 over 2 is 4. Just to illustrate how we do that and how we'd incorporate the nitrogen, subtracting 1 from the actual, and halogens adding 1. Now to illustrate this, I'm first going to do example G. So scroll down to example G. We're going to do that together first and then go back to start with A and B. The very first thing I'm doing is calculating my IHD. I'm going to take my number of carbons, multiply by 2, and add 2. 8 times 2 plus 2 gives me 18, minus an actual of 16. No nitrogens or halogens, forcing me to adjust the actual value. Over 2, that comes out to 2 over 2, which is 1 IHD. Now, theoretically, that could be 1 pi bond or 1 ring. But what I'm going to have you do is assume pi bond, as opposed to assuming ring. If there was a ring and it's substituted, what can happen is you get into this territory where you'd have diastereotopic protons on the ring, which would then cause really crazy splitting and the spectrum gets really ugly. So because the spectrum can get ugly with cycloalkane rings, we're going to assume pi bond. And if that ever does not work out, like assuming pi bond just doesn't play out nicely, then we can default back to ring. Now, I've got 1 IHD, probably meaning there's 1 pi bond present. We could actually distinguish between C double bond O versus, say, an alkene pi bond. And this might be relevant if we have oxygens in the molecular formula. And how we do that is we look for vinyl signals. Now remember, vinyl protons would shift 4.5 to 6.5 approximately. They would likely have 1H integrations, and their splitting might be doublet, doublet of doublet, or doublet of doublet of, something else. If we saw those types of signals, that'd be maybe indicative of there being a carbon-carbon pi bond. Notice how the graph doesn't extend beyond 5 here, so there's no vinyl signals. Given that there are no vinyl signals, it's more likely that the IHD represents a C double bond O in this example. Okay. Now, I find that if we don't know that there's double bonds present, we might have this bias towards making single bonds. So just because we know that there's possibly a double bond, given that the IHD is 1, that's huge. Okay. So we likely have a C double bond O. That's a piece to our puzzle. Now we need to generate an anchor point. So I'm going to start with my most downfield shifting signal. And because I have an oxygen in my molecular formula, I'm going to Q into this 3 to 5 range. That's right, I have a proton on a carbon bonded to oxygen, 3 to 5. So given that the 2 hydrogen signals in that region, I'm going to say that's likely bonded to my oxygen atom. Okay, that's my anchor point. Now I use splitting and integration. Given that that signal is a triplet, that means that there's 2 neighbors on the adjacent carbon. So I'd be neighboring a CH2. Notice I read that triplet as 2 neighbors. Or if I say, have a sextet, I'm going to read that as 5 neighbors total. Okay. So notice that right now I've gotten all this information from 1 signal. That's the power of reading. We don't need to go across the spectrum and annotate willy-nilly. We read the spectrum, generate your anchor point, and build. Now, coming back to that CH2, I've asserted that there's a CH2 just based upon that signal there. What I now need to go and do is find a 2H integration to correspond that. This is the only other 2H integration, so that represents that CH2. It's a sextet, so there's a total of 5 neighbors. Now, I've already got 2 of those 5 neighbors accounted for. So to give there a total of 5 neighbors, I would need to add in a CH3. 2 and 3 make 5, 5 neighbors. This CH2 is our sextet. Now, that being said, I need to go and find in the spectrum the 3 hydrogen signal, which I anticipate to be a triplet split by the adjacent CH2. And I find that 3H triplet. You also, as you're going along, want to, mark the signals that you've already reconciled. Okay. Now, at this point, I've built that piece to its completion. And what I also want to acknowledge is that on the other side of this oxygen atom, I'm not going to bond to a carbon with any hydrogens. So I need to bond to a carbon with no hydrogens, because if there was a carbon with hydrogens there, I'd see another signal in that 3 to 5 region, which I do not. Now, the only other signal that we have yet to reconcile in this example is our 9H singlet. And to have 9 hydrogens that are equivalent, you would have to have 3 methyl groups branching off the same carbon. In other words, a terp-butyl terminus. Now, at this point, we have our terp-butyl group, our O with the propyl chain, and our C double bond O. Those are the pieces to our puzzle. We now need to put these pieces together. The way that I would do that is to attach the O propyl group to the C double bond O, and also the terp-butyl group there, because that means this carbon has 0 hydrogens. We know that the oxygen needed to connect to a carbon with 0 hydrogens. And then we have our terp-butyl group coming off there. And in this particular example, there's no way to arrange these pieces in another fashion. Okay, in other examples, you might have multiple pieces and there's multiple structures you can make. But in this example, the only way to combine those is into this structure here. So to recap that quickly, IHD was 1. We're going to assume pi bond. We then tried to distinguish if it's a vinyl pi bond, carbon-carbon pi bond, or C double bond O. There was no vinyl signals that indicated it's possibly a C double bond O. We got our anchor point of 2 hydrogens. That's in the oxygen region, so CH2 is bonded to our oxygen. It's a triplet, so that means that there's 2 neighbors. I drew in a CH2. I then needed to go and find that CH2, and it was a sextet. That means that there's a total of 5 neighbors. We already had 2 accounted for here. So to give us a total of 5, I had to put in a methyl group. That would give me a sextet, 5 total neighbors. And I drew in the CH3. I would then need to go and find its signal to reconcile and validate that it's there. And it did appear as a 3H triplet, which validates that connectivity I drew in. Then the other signal was a 9H singlet. That's a terp-butyl group, classic terp-butyl group. I then put those pieces together into a proposed structure. Okay. So we're now going to go through a lot more examples, so strap in. I know this video might be a slightly longer video than normal, just because spectrums take time. We're now going to do example A. Let's start with the IHD. Theoretical is the number of carbons times 2 plus 2. That would give me 14 minus the actual. Notice the nitrogen will subtract 1 to give an adjusted value of 14. 14 minus 14 over 2 is 0. So we know that there's no pi bonds, no rings. That's still helpful data. Starting with the most downfield signal, notice it's a broad singlet. And it's also not, say, around 12 as a broad singlet as we'd expect for carboxylic acid, and it's, not around 9 as we'd expect for phenolic OH. So this is probably an OH or NH proton bonded to an sp3 oxygen / nitrogen, which, remember, are very variable 2 to 7. That is to say, I cannot use the chemical shift of that broad singlet to determine if it's an OH or NH. Rather, what I need to do is I need to look at the number of signals respectively in the oxygen / nitrogen region. So watch this. Proton on a carbon bonded to oxygen is 3 to 5. Proton on a carbon bonded to nitrogen is going to be 2 to 3. We're going to use the number of signals in each region to determine if it's an OH or NH. And here's a short little breakdown of this. If in the oxygen region we saw 1 signal and 3 signals in the nitrogen region, that means that the second bond to oxygen is the hydrogen. That's how I determine OH. If it were an NH, alternatively, you'd have 2 signals in the oxygen region and only 2 signals in the nitrogen region. That would indicate we have an NH proton. Okay? So we can't assume OH versus NH. Now, as we look in those regions, oxygen versus nitrogen will also exclude in our analysis the broad singlet. So that's the first thing I'm doing. I'm going to look at the oxygen region, and I see that there's 1 signal. So the oxygen is attached to a CH2 group. And then in the nitrogen region, you'll notice that there's 3 signals. We have the 1H, the 2H, and the 3H. That means that the nitrogen's bonded to a methyl group, it's bonded to a CH2, and then to a CH carbon. That being said, nitrogen only makes 3 bonds and it's got 3 carbon attachments, so it can't have a hydrogen on the nitrogen. We would instead have an OH proton. So that aligns with what we saw here. 1 signal in the oxygen region, 3 signals in the nitrogen region. Therefore, it's an OH proton as opposed to NH proton. Okay, that's the very first thing that we need to do. If we assume OH versus NH, that can get us into trouble. Now, the next thing I'm going to do is I'm going to build. So maybe I start with my oxygen atom. The oxygen is bonded to a CH2 group, given this signal here. It's a triplet, therefore it's adjacent to another CH2 group. So I need to go in the spectrum and find the 2H integration. The only other 2H integration is the one here in the nitrogen region, which is also just split into a triplet. Given that that signal's in the nitrogen region, it needs to be bonded to our nitrogen atom, and you'll notice that the CH2s are just mutually and exclusively splitting each other into triplets. From there, I'm now going to build off the nitrogen atom. In the nitrogen region, we have a CH right here, and if you zoomed in, you would see that that CH is split into a septet, which means that there's 6 adjacent neighbors, and to get 6 adjacent neighbors, we'd have to have an isopropyl nature to that CH bonded to 2 methyl groups. For that to be the case, I'd also in my spectrum have to find a 6H doublet, and I do see that 6H doublet, which is representing those 2 methyl groups coming off the CH. And finally, the last signal to reconcile is this 3 hydrogen signal, which is in that 2 to 3 range, therefore it will be a methyl group coming off the nitrogen atom. Okay. So professors at UNC have done this in the past fairly consistently, where they have both a nitrogen and oxygen in the molecular formula, and you have to determine OH versus NH. We cannot use that chemical shift alone. We could use the chemical shift alone to distinguish OH versus NH if it were something like this, carboxyl or phenolic OH, but given that the oxygen is sp3, a little bit more variable. So we have to look at the number of signals in each of those regions respectively. Okay. Now we're going to illustrate that same process here, another OH versus NH determination. First, we begin with the IHD. IHD, number of carbons times 2 plus 2 would give me 14 for my theoretical value. I then subtract the actual, but I notice that there's a nitrogen, so I subtract 1 from my actual value to give me an adjusted actual of 14 over 2. That comes out to be 0. Okay, 0 IHD, no pi bonds, no rings. Looking at the most downfield signal around 5.5, we see a broad singlet that could represent an OH or an NH. So now we distinguish between the two. I look at the oxygen chemical shift region of 3 to 5 versus the nitrogen region of 2 to 3. Now what's interesting about this example is in the oxygen region, there's technically 3 signals. So what I'm going to do is make this assumption that the 2 more downfield shifting signals are associated with the oxygen, and the one upfield relative to that, the 3H singlet, is probably bonded to the nitrogen, and it's just shifting past that anticipated region. That's not unheard of. So given that I have 2 signals in my oxygen region, the oxygen can't be bonded to a proton because it's already got its 2 bonds, and I have 2 signals in the nitrogen region, which indicates that the 3rd bond to my nitrogen is likely the NH. So 2 signals in the oxygen region, 2 signals in the nitrogen region, that would validate that we have an NH as opposed to an OH. So now I'm going to read downfield to upfield. I'm going to start maybe with the signal in the oxygen region. Oxygen is going to be bonded to a CH, and that's split pretty complexly. Looks to be split into a septet, indicating the presence of 6 adjacent neighbors. And I do have this 6H doublet all the way upfield here. That would validate that there actually is an isopropyl group. 1H septet, 6H doublet, classic isopropyl group. Then I'm going to build off the other side of the oxygen. Looking in the oxygen region, I've got a CH2 group, which appears to be split into a triplet. That means I have a CH2 off my oxygen, which is then neighboring another CH2 group. So now I need to go and find the CH2 in the spectrum, and the only other 2 hydrogen integration is this one here. And that 2H is bonded to the nitrogen, given where it's falling chemical shift-wise. And that's why it's just a triplet, meaning the CH2 groups again are mutually and exclusively splitting one another. Now we said that we have an NH proton, so at this point I'm going to plug on that hydrogen to the nitrogen. And the only other signal that we haven't reconciled yet is this 3 hydrogen singlet, which is coming off the nitrogen. I know that's shifting a little bit past 3. Usually they're 2 to 3 if it's a proton on a carbon bonded to nitrogen, but it's not unheard of to shift past 3. And so here's our structure. CH3 on the nitrogen, 2 CH2s intervening the nitrogen and oxygen. Then on the other side of the oxygen, we have the isopropyl group. Again, what was kind of crucial to this determination here was assuming that the two more downfield shifting signals in that 3 to 5 range were associated with the oxygen, and making the assumption that the other one can't be associated with the oxygen because, well, oxygen already has two groups bonded to it. Okay. Now, if you found that a little bit hard to follow with the OH versus NH determination, go back and look at that / take time to really tease apart how I went through that. You might have to do that on your exam. Okay. Now we're going to move on to example C. Starting with the IHD, we're going to take the number of carbons times 2 plus 2. That would give me 12 for my theoretical value, minus 10 for my actual. There's no nitrogens or halogens, forcing me to adjust that, over 2. It comes out to be an IHD of 1. Now that could represent one pi bond or one ring, but we'll assume one pi bond. And I'm not really seeing any vinyl signaling in that 4.5 to 6.5 range, so likely not a carbon-carbon pi bond. What I am seeing is a signal close to 10. Now remember, around 10 is where you'd have an aldehyde proton shift. So that's likely an aldehyde functional group. That confirms that the IHD is the C double bond O. Now you also want to acknowledge that there's two oxygens present, and I've used one of them. So given that that's a triplet, that means that there's an adjacent CH2 group coming off. So what I'm now going to do is scan my spectrum for a CH2 integration, and there's 3 of them. Now, I see 2 of them right here. One's a doublet, and then one's a triplet. Now, I'm probably going to say that the one that's a doublet is likely the CH2 here, because I know that CH2 has to be at least a doublet split by that one hydrogen. Now, given that that CH2 doublet signal pictured here is in that 3 to 5 range, what I'm going to assume is that the oxygen is actually on the other side of that CH2, giving it that downfield chemical shift. That also blocks splitting, such that the CH2 is only influenced by the CH of the aldehyde. Then I'm going to build on the other side of my oxygen atom. That's probably going to be the next most downfield CH2 coming off that. So there's going to be a CH2 coming off the oxygen pictured by this signal here. It's a triplet, which means that there's another adjacent CH2 splitting it into a triplet. I now need to go and find that CH2 in the spectrum, and the only other CH2 integration to reconcile is the CH2 sextet. If that's a sextet, there's a total of 5 neighbors. Now I've already got 2 of my neighbors accounted for. So to get there a total of 5 total neighbors, I'd have to add in a methyl group. And that would then mean I should find in my spectrum a CH3 triplet. And I do see that all the way to the right. Okay, so to recap that, we had one IHD indicating one pi bond. I saw the aldehyde signal around 10. That is our IHD. It split into a triplet, so there was a neighboring CH2. I then had 3 CH2 integrations, but I saw one that was a doublet, which means it could be split by the aldehyde hydrogen. Now, given that that's just a doublet and it's in the oxygen region, I'm going to plug in the oxygen next to that CH2. Then on the other side of the oxygen, I'd likely have this signal here, CH2 triplet, also in that 3 to 5 range. Because it's a triplet, there's a neighboring CH2. So I went and I found that CH2 in my spectrum, saw that it was a sextet, total of 5 neighbors. To give a total of 5 neighbors, I had to put a CH3 to the right of that. That means that I should find a CH3 triplet in my spectrum, and I do. Therefore, this is our guy here, aldehyde, CH2, and then a propyl group, spectrum C. All right, solving spectrum D here. Starting with the IHD, I take my number of carbons times 2 plus 2, that would give me 22. 10 times 2 plus 2, actual number is 12. No nitrogens or halogens, forcing me to adjust that. That would give me 10 over 2, which is 5 IHD. Now, 5 IHD is likely representing a benzene ring, constituting 4 of those IHD, plus a pi bond. Okay. Now, if I ever determine that there's a benzene ring, given my IHD, what I like to do is go ahead and go to the aryl region. That's at 6.5 to 8 region, aryl protons. And what I do is I look for the substitution pattern, if it's ortho, meta, para, or if it's monosubstituted or trisubstituted. Now I'm seeing 2 signals in that region, both of which appear to be doublets. And remember that 2H doublet combo would be your para disubstituted ring. Now that doesn't tell us what the substituents are, it just tells us that the ring is substituted para, and that takes care of the hydrogens on the ring. From there, I might think about this other pi bond, and what I'm going to do is check that vinyl region of 4.5 to 6.5, and what I'm seeing is signaling in that vinyl region. Specifically, I see a 1H doublet of triplets, and then here I've annotated that there's overlapping doublet of doublets. Okay, given that we're seeing that vinyl region light up, there's likely a carbon-carbon pi bond present. And there's 3 of those 1H signals, so that means I've got something like this. Now, pausing for a second, let's go down here and make a quick comparison. The hydrogen here potentially can be split if there's a neighboring group. For example, if there was a CH2 here, this hydrogen would be a doublet of triplets. If we attach to a carbon with no hydrogens and or an oxygen atom, then this hydrogen would just be a doublet of doublets. And of course, these other ones here, protons on the double bond, would just be doublet of doublets inherently. So when you're looking at that vinyl region, the 3 signals there tells you have 3 hydrogens, and then if one is more complex than just a doublet of doublets, that would represent the hydrogen here and indicate that there's splitting coming from the other side as well. Doublet of triplets. So I've just asserted that there's a CH2 off my alkene pi bond. I would then want to look in my spectrum for a 2H integration, and there's only one of those. And notice that it's also a doublet. That means that it's just being split by that one hydrogen, and I need to block splitting from the right side. I'm also going to acknowledge that I haven't used my oxygen yet, and in the 3 to 5 range is typically where I'd see protons on a carbon bonded to oxygen. So it's likely the case that given the chemical shift is in the oxygen range, and I need to block the splitting from the right side, that I'm going to bond an oxygen to that CH2 group. I'm then also going to acknowledge that I see no other signals in the 3 to 5 range indicating that I need to block splitting here. And one way to do that would be to connect the oxygen directly to the benzene ring. So you'd have an oxygen, your CH2, and then your alkene pi bond with 3 hydrogens, like that. Those are ugly hydrogens. Let's redo that. 3 hydrogens off the alkene. Now, the only other signal to reconcile is the 3H singlet here. And remember that in the 1.5 to 2.5 range, that's where you'd likely see protons on a carbon neighboring a pi system. And the chemical shift and the fact that it's a singlet would validate attaching that CH3 directly to the benzene ring. Okay. Quick recap, 5IHD meant that we had a benzene ring and likely another pi bond. If I have a benzene ring, and I determine that from the IHD, I'm going to look at the aryl region to see if it's ortho, meta, or para. Para is a 2H doublet combo, which we saw. So I created para disubstitution. From there, I thought about my pi bond. I saw vinyl signaling. So I'm going to create a carbon-carbon pi bond, and I'll plot as many hydrogens on that pi bond as I see vinyl signals. 3 vinyl signals. And if there was a carbon off the pi bond with hydrogens, that would split the hydrogen closest to it. And if there wasn't, well, then that hydrogen would just be a doublet of doublets. So because one of those was a doublet of triplets, I attached a CH2 off here such that that hydrogen would be a doublet of triplets. I then needed to go and find that CH2 in my spectrum. I could look for a doublet potentially, but definitely looking for a 2H integration, which happens to be a doublet and in the oxygen region. Therefore, I'm going to attach the oxygen to that CH2. There were no other signals in the oxygen region, so I attached the oxygen directly to the benzene ring, because as I connect to the benzene ring, there's 0 hydrogens on that carbon. Last signal was a CH3 singlet in that 1.5 to 2.5 region, proton on a carbon adjacent to a pi system, so I'll attach that directly to the ring, and I've solved for the compound represented by spectrum D. All right, moving on to example E. All right, for example E, we're going to start with our IHD value. Calculating that, we take the number of carbons times 2 plus 2. 10 times 2 plus 2 gives me 22. There's 12 actual hydrogens, no nitrogens or halogens, forcing me to adjust that. That would come out to 5 IHD, likely representing that we have a benzene ring plus 1 pi bond. So I'm going to look in that benzene region, and what I see is this 5H bonfire. Remember that 5H bonfire is what we could expect if we had a monosubstituted ring. We're going to have a benzene ring with 1 substituent. Then I'm going to think about that other pi bond. Now, I'm not seeing any convincing vinyl signaling. I've only got one signal in that range. So I might look at the signal downfield to further distinguish. And in that downfield region around 10, I see a 1H signal that likely represents an aldehyde. That would probably be the best validation for the other pi bond. Okay. So we've got this aldehyde functional group, and notice it's split into a doublet. That means that I'd have to have one hydrogen on the neighboring carbon. I'm then going to find a 1H integration, and I see a 1H integration here. I also see that it's just a doublet. That means that whatever attachments are here, they cannot be causing any splitting. Splitting is mutual and exclusive between the aldehyde hydrogen and that CH hydrogen, which are splitting each other into a doublet. So when I think about what those attachments could be, one attachment might be the benzene ring. I'm also going to acknowledge I haven't used my other oxygen. That being said, 3 to 5 is the typical oxygen region, but if there was an oxygen here, it would be likely that that signal would shift potentially past the oxygen region, because I've got the inductive effect from the oxygen and the inductive effect from the C double bond O and potentially the inductive effect of the benzene ring. So I'm going to attach my oxygen to that CH carbon. That's validated here by the chemical shift. Okay, got these signals figured out so far. Then on the other side of the oxygen, if there's protons on a carbon there, they'd shift in the 3 to 5 region. I am seeing a signal in that region, specifically a 2H quartet. So it's a CH2 split into a quartet, which would indicate the presence of 3 neighbors. Now, I would then have to go and find that CH3 in the spectrum, and it would have to be a CH3 triplet. And I am seeing a 3H triplet here. That would validate the connectivity we just made there. And at that point, we've reconciled all the signals, which means this other attachment to our CH carbon must be the benzene ring. In other words, off the benzene ring, we have a CH carbon, which is then attached to the aldehyde and to the O with the ethyl chain. That would be our compound there. Essentially, I just made this attachment here to the benzene ring. Okay, quick recap, 5-IHD benzene ring plus 1 pi bond. We have our 5H bonfire, which is a monosubstituted ring. Didn't see any convincing vinyl signaling, so I looked at my most downfield signal, around 10, that's where an aldehyde would shift. Given the fact that it's a doublet, it was adjacent to a CH carbon. I then looked for 1H integration to relate that, and it was just a doublet. And it's also really far downfield, so I knew that the CH can't be split by any other groups besides the aldehyde hydrogen. Given that it was that far downfield and I had another oxygen, I attached the oxygen atom to that. Then on the other side of the oxygen, I look in the 3 to 5 range, I saw a 2H quartet, which means that I had a CH2 bonded to my oxygen. Given that it was a quartet, there was likely an adjacent methyl group. And I looked in my spectrum for a 3H triplet, and I saw that. So I terminated that component. At that point, I'd reconciled all the signals, which means that the other attachment to the CH needed to be the benzene ring. Okay, kind of a fun example. All right, moving on to example F. Check this out. We're going to start with our IHD. Number of carbons times 2 plus 2 would give me 12. 5 times 2 plus 2. Number of actual hydrogens is 8. No nitrogens or halogens, forcing me to adjust that. Divided by 2. That comes out to be 4 over 2, which is 2 IHD, likely representing the fact that we have 2 pi bonds present. Now, in the vinyl region, I am seeing some signals here. So I've definitely got carbon-carbon pi bond present, and there's got to be 2 hydrogens. Okay, we'll come back and reconcile that, but I know that there's a carbon-carbon pi bond present. What's really going to jump out at me is the signal most downfield is a broad singlet near 12, and remember, that would be indicative of a carboxyl group. Now, we don't necessarily know where that carboxyl group is yet because it's not split, so I can't assume connectivity there. But that's a piece to my puzzle. What I do from there is probably look at this vinyl region. Now, I've only got 2 vinyl protons. One is a doublet of quartet, and one is a doublet of triplet. Now, to get a hydrogen that would be a doublet of quartet, I would have to attach a methyl group to that carbon that would split it into a quartet. And then there would have to be on the adjacent carbon 1 hydrogen to split it as well. That's how I'd get a doublet of quartet. Okay, so that reconciles this one. To get a doublet of triplet, I would have to have a proton on the alkene, adjacent to a CH2. So that splits it into a triplet, and then it's split into a doublet by the other hydrogen there. Okay, I'm going to recap that down here just to really formalize that. We only saw two signals in that vinyl region, so only two hydrogens on the alkene. And to have a doublet of quartet, I would need to have a methyl group split it and an adjacent hydrogen of the alkene split it. Then for this hydrogen here to be a doublet of triplet, it's already split into a doublet by that one hydrogen, but then I'd have to have two hydrogens on the neighboring carbon to also split it into a triplet. Okay? So now we're going to work from that CH2, that's our building point. We had our 1H, which was a doublet of triplet that told us that there was a CH2 here. I'm then going to go and find an integration of two hydrogens, and I see that that's just a doublet, meaning that whatever we attach to here cannot cause splitting, because it's only split by the one hydrogen of the alkene. And let's also reconcile to that the three hydrogens that we already included there, that's the 3H doublet down here. And so at this point, we've actually reconciled all of the signals. So we have our carboxyl group, we have our alkene with the methyl group coming off one carbon and the CH2 off the other carbon, which means that they're likely going to connect together. In other words, we're going to have something that looks like this. Okay, we have our one hydrogen doublet of quartet, our one hydrogen doublet of triplet that attach to a CH2 group. And then we need to block splitting from the right side such that the CH2 is only split by the hydrogen of the alkene. And I could connect that to the C double bond O. How that's further validated is usually a proton on a carbon neighboring a pi system would be 1.5 to 2.5. I'm seeing that 2H doublet around 3, which could indicate that that's a CH2, experiencing an inductive effect from two pi systems, okay, which is the case here. Kind of a funky example. It's a little bit trickier with our vinyl protons when we have splitting into a doublet of quartet or doublet of triplet, but you would just do that incrementally, focusing on how do I get that to be a doublet of quartet? How do I get that to be a doublet of triplet? And then to read past that, we'd have to use splitting to our advantage. And the fact that that's just a doublet indicates that we need to block splitting from the right side, meaning we have to bond to a carbon without hydrogens. And conveniently, the C double bond O carbon was a carbon without hydrogens. All right. We already did G as our intro example, so we're going to move on to example H. All right, looking at H, we're going to begin with the IHD. Number of carbons times 2 plus 2, 13 times 2 plus 2 would give me 28. 28 theoretical value, number of hydrogens is 18. No nitrogens or halogens forcing me to adjust that. That comes out to 10 over 2, which is 5. Likely meaning that we have a benzene ring constituting 4 of those IHD plus another pi bond. So I'm going to look in that benzene region first and foremost to figure out if I've got ortho, meta, para, or if it's mono-substituted. I see that classic 2H doublet, which would be indicative of a para di-substituted ring. So I'm going to have a benzene ring, and there's a substituent on either side, 1,4 substituted. I'm then going to start with my most downfield signal, keeping in mind I have one pi bond, and I've got two oxygens in my molecular formula. Now a broad singlet around 12, classic carboxyl group. Classic carboxyl group. Now notice as we reconcile that, that's going to take care of both of our oxygen atoms and our fifth IHD. Okay. Now, I don't know if that's directly connected to the ring or not, but I can figure that out based upon the other signals. Now, given that I've used both of my oxygens, I know that the downfield shifting of the next most downfield signal there cannot be a result of being directly connected to an oxygen, but rather being adjacent to our pi systems. We have the C double bond O of the carboxyl group and the benzene ring itself. Now remember, proton on a carbon adjacent to one pi system would make it go 1.5 to 2.5. Given that the CH2 here is shifting closer to 4, that's probably a CH2 adjacent to two pi systems, and therefore, with two connectivities to pi systems, it would just be a singlet. That's enough of a validation to say we probably have the CH2 connecting to the benzene ring, which is blocking splitting on that left side, and then I'd also wedge it between the carboxyl group, such that we have an inductive effect from the C double bond O and from the benzene ring, which would predictably shift that past the normal 1.5 to 2.5 range if there was only one pi system acting on it. Okay. That's how I deduce that. We always track if we've used our electronegative atoms or not, and then we think about what else could cause downfield shifting. Well, we've got pi systems present. I'm then going to make the assumption that the next most downfield signal is likely going to be a proton on a carbon coming off the ring directly, because that's the other inductive effect we have present. Now that CH is split into a quintet, which means that there's 4 total neighbors. And one way to get 4 total neighbors is to have 2 CH2 groups. The other way to get 4 total neighbors is to have a CH3 and a CH. That being said, it's likely not the CH2 is attached because I'm not seeing any other 2H integrations or a 4H integration. It's more likely this situation here where we have a CH and a CH3. Now that's also validated in the spectrum because I've got this 3H doublet. That could be a methyl group coming off that CH. And then I'm also seeing another 1H integration. So off that CH2 of our benzene ring, which is this signal, I've got 4 neighbors, which in this case is a methyl group and a CH, validated by these signals here. Then this CH is just labeled as a multiplet, which is kind of a cop-out way of saying that it's complexly split. So it's receiving splittings from multiple directions. To figure out what that's attached to, I would maybe look for a doublet signal. And the last signal that we have available to us is the 6H doublet. And 6 hydrogens is going to equate to 2 methyl groups. Okay, so that 1 hydrogen there is actually even more complex than a septet. It's like a septet of doublets, really. All right, to recap this one, because this one's a little bit more tricky, our IHD was 5, indicating the presence of a benzene ring and another pi bond. I looked at the benzene ring to figure out if it's worth a meta-para. It is para-disubstituted, substituents on opposite sides. I then looked at that most downfield signal, broad singlet around 12 indicated a carboxyl group, and I'm not going to assume that that's connected to the benzene ring. I need to problem solve to figure that out. But that would account for our pi bond, and so we've already satisfied our IHD, and drawing the carboxyl group gave us our 2 oxygen atoms. From there, I'm going to look at the next most downfield signal, always reading downfield to upfield, and because I've already used my 2 oxygen atoms, that is going to be affected by pi systems, giving it its downfield shift. The fact that it's a singlet means that it needs to be blocked on either side, and to get that far downfield of a shift, it would have to be between 2 pi systems. That's why I wedged that CH2 in between the benzene ring and the carboxyl group, which validated and finalized where that carboxyl group would be located. Then I started on the other side of my benzene ring. The next most downfield signal would have to be impacted by the benzene ring. That was a CH split into a quintet, so there needed to be 4 neighbors, and given the other signaling I saw, that would validate a CH3 and CH connectivity. But in other cases, remember, a quintet could potentially be a CH2 and another CH2. So I drew in my methyl set and my CH, giving me these 2 signals here. Then to figure out what was bonded to this CH, I looked at its splitting pattern, saw it was complexly split, and I scanned my spectrum for a doublet because likely whatever's bonded to that CH would be a doublet. And I saw my 6 hydrogen doublet, which is equating to 2 methyl groups that are equivalent and coming off that carbon. All right, definitely an exam caliber structure. We're now going to move on to example I. Example I. Okay, starting with our IHD. Number of carbons times 2 plus 2 would give me 24. 11 times 2 plus 2. Minus the actual, which is 14. No nitrogens or halogens, forcing me to adjust that over 2. That comes out to be 10 over 2, which is 5. Likely meaning that we have a benzene ring plus a pi bond present as well. Okay, so I'm going to go to that aryl region first and foremost to reconcile the signaling and the substitution of my benzene ring. And again, we're seeing that classic 2H doublet indicative of a para-disubstituted ring. So substituents on opposite sides. I then see the most downfield signal here is around 10. Now, that could be an aldehyde. Aldehyde shift around 10. And you'll notice that that's just a singlet, which means that it has to connect to a carbon with no hydrogens. And in doing so, by creating that C double bond O of my aldehyde, I've used my oxygen and satisfied my other IHD. Now, given that I need to connect to a carbon with no hydrogens, one way to do that would be to attach to the benzene ring. For now, I'm going to make that assumption, and that will be proved correct if the other signals play out nicely. Let's say that I make this assumption that the aldehyde's on the ring, and then these don't reconcile nicely. Then maybe the aldehyde's not attached to the benzene ring, but for now we're going to run with the fact that it's attached to the ring. What I'm then going to acknowledge is because I've used my oxygen atom, the next most downfield shifting signal is likely coming directly off the benzene ring there. And what we're seeing is that that signal is in the predictable range of 1.5 to 2.5, so proton on a carbon neighboring 1 pi system. So I likely have a CH2 coming off my benzene ring. And it's split into a doublet, which means that there's one adjacent neighbor. So my CH2 off my ring is adjacent to a CH. Now I'm going to go and find that CH in my spectrum, looking for my 1 hydrogen integration, and I see that it's a multiplet, meaning that it's complexly split and split by whatever is here and adjacent to the CH2 group off the ring. And I look at my last signal, seeing a 6 hydrogen doublet indicative of 2 methyl groups that are equivalent. That's enough to cap this chain by attaching 2 methyl groups to our CH. Now, because those signals played out nicely, that validates that connecting the aldehyde to the ring was correct. Okay. Now, I don't think this one requires a recap, so we're going to move on to the next example. All right, example J. Example J, starting with our IHD, taking the number of carbons times 2 plus 2, that would give me 16, minus the actual of 12, no nitrogens or halogens, forcing me to adjust that over 2. That comes out to be 4 over 2, which is 2. We're going to assume that likely means 2 pi bonds. Now, looking in the vinyl region, which is also where these most downfield shifting signals are located, I'm seeing that light up. That means I've got a carbon-carbon pi bond present. And I'm seeing 1, 2, 3 vinyl proton signals. So that means I've got 3 hydrogens off my alkene. And notice that they're all doublet of doublets. What that means is on this right side, I need to connect to a carbon with no hydrogens and or maybe the oxygen. Remember, if I had, say, protons on an alkene pi bond and I connected to a carbon with a hydrogen, then this hydrogen would be split by that adjacent carbon and the other 2 hydrogens. So as drawn here, this would be a doublet of doublets. Because all of those were just doublet of doublets, I knew that off the alkene, I need to connect to a carbon with no hydrogens and or the oxygen to give that hydrogen just a doublet of doublet pattern. Okay. Now, at this point, I have to kind of pause here. I don't know exactly what we're going to connect to because there's no validation for what that might be. Okay. But what I'm going to acknowledge is that in the oxygen region of 3 to 5, there's no signals there. Okay, because I haven't used my oxygen yet, I might look to that region. Proton on a carbon bonded to oxygen is 3 to 5. Because there's no signals in that region, I'm going to assume that this CH2 here is influenced by a pi system, and also it means my oxygen needs to be bonded to a carbon with no hydrogens. And what that means is we might have a C double bond O, because we haven't used our second IHD. One of our IHD was accounted for by the carbon-carbon pi bond, and the other might be a C double bond O. Now, that C double bond O guess is further validated by in this region here, 1.5 to 2.5. What we see a signal, we see a 2H doublet, meaning that if we assume there's a C double bond O, we could have a CH2 off the C double bond O that's split into a doublet. Split into a doublet means that there's an adjacent CH. I then go and find that 1 hydrogen. I see it's complexly split. And then I see a 6H doublet indicating 2 methyl groups that are equivalent. Therefore, there could be 2 methyl groups coming off that CH carbon, giving us the 6 hydrogens that are equivalent and split into a doublet, and ensuring that that 1 hydrogen is very complexly split. Okay. And then we connect our pieces, meaning we likely have our C double bond O with the CH2 and the CH, that component there. And then on the other side, we could have our alkene pi bond. And why that connectivity works is we needed, the alkene to connect to a carbon with no hydrogens, and as drawn, we connected to a carbon with no hydrogens. I think this is another prime example of where IHD is particularly important, because knowing that there was 2 pi bonds helped us figure out that because there was no signals in the oxygen region, our oxygen needed to connect to a carbon with no hydrogens, nor did we see any broad singlets, which would be indicative of an OH group, because I didn't see any signals here, nor a broad singlet. Oxygen doesn't have any protons directly, and it's also bonded to a carbon with no hydrogens. That validated our second IHD, and then I built off of that C double bond O here to create the other connectivity. Okay. Now let's also acknowledge this. If we had said that we had our carbon-carbon pi bond, okay, and then we maybe built something like this, if we assumed it was the oxygen, which is an incorrect assumption, then the other signal coming off that, the chemical shift wouldn't be appropriate because that would have to be 3 to 5. If you have a proton on a carbon bonded to oxygen, it definitely needs to be past 3. And notice we had no signals definitely past 3. That means that the CH2 doublet had to be adjacent to a C double bond O, and it could not be, say, immediately off this carbon-carbon pi bond. Okay, that would also have the chemical shift of that. But then if I attach the CH2 there, that would be a doublet of triplets, and we knew that it had to be just a doublet of doublets. Okay, so kind of a tricky example, but really it gets at this idea of we cannot assume connectivity, rather we have to deduce connectivity. Okay. All right, moving on to example K. Example K. Looking at our IHD, number of carbons times 2 plus 2, that would give me 22 for my theoretical, 10 times 2 plus 2, 12 actual over 2. That comes out to be 10 over 2, which is 5, likely meaning we have a benzene ring plus 1 pi bond. So I'm going to look at the benzene region, figuring out the substitution of my benzene ring, and I'm not seeing an ortho pattern. I'm not seeing a meta pattern or a para pattern. Remember, ortho would have 4 signals, no singlet. Meta would have 4 signals and a singlet. Para was 2H doublet, and our mono-substituted ring would be that 5H bonfire. In that aryl region, I'm seeing none of those patterns, which likely means that this is a tri-substituted ring. Okay. Now, if I thought about having 3 substituents, in order for them all to be singlets, what I'd have to do is alternate substituents around the ring, such that there is no hydrogen adjacent to another hydrogen on the benzene ring. Okay, so likely a tri-substituted ring. What I'm then going to do is look at the most downfield shifting signal, which is appearing around 10. That would probably be an aldehyde, characteristically around 10. Because that's just a singlet, that means I need to connect to a carbon with no hydrogens and or my other oxygen. But it likely can't be the oxygen because I'm noting that there's actually a 1H broad singlet here. So likely the case that we're connecting to a carbon with no hydrogens, which might mean that we could attach that to the ring. Let's make that assumption, roll with it. If the other signals don't work out, then that's incorrect. But if they do, that is correct. Now, I've reconciled my 1H singlet, got my tri-substituted ring. I'm now going to look at my broad singlet. What I'm going to recognize there is that it cannot be directly bonded to the benzene ring, because if I had OH directly bonded to the benzene ring, that's likely going to be around 9. So what this means is we have an OH proton, broad singlet, and that's just got to be connected to another sp3 hybridized carbon. Now in the oxygen region of 3 to 5, I'd probably find the connectivity to that oxygen. And what I'm seeing here is a 1H quartet, which means that there needs to be a total of 3 neighbors to make that into a quartet. So to get 3 neighbors, I could potentially have a methyl group. And what I'm noticing is the other 2 signals are methyl signals, and therefore one of those methyl groups is this one. And probably it's this one here, the 3H doublet. That is the methyl group coming off the CH, because I'd anticipate that to be split by the CH into a doublet. Now that means the other connection point to that CH carbon is probably the benzene ring. And why it's probably the benzene ring is it's appearing pretty far downfield, right? Okay, it's almost to the edge of that oxygen region, probably indicating that not only do we have the oxygen withdrawing, but we get attached to the benzene ring directly, and that would also withdraw from the CH. That brings us to the very last signal that we haven't reconciled, which is a 3-hydrogen singlet, and it is in that 1.5 to 2.5 range, which could be a validation for attaching the methyl group directly to the benzene ring. Okay, I'm going to recap that quickly. Calculator IHD, it was 5. That means we have a benzene ring constituting 4 of them in 1 pi bond. I looked at the aryl region. I didn't see ortho, meta, para, or monosubstituted patterning to my signals, so likely meant a tri-substituted ring. To make them all singlets, I had to alternate those substituents going around the ring. I looked at the most downfield shifting signal. It's a singlet, indicating probably an aldehyde given the chemical shift, and I know that it has to connect to a carbon with no hydrogens, which would maybe be a validation for connecting it directly to the benzene ring. I then saw a broad singlet, 1H broad singlet, which is definitely an oxygen, OH. If it were off the ring directly, it would be around 9, but it's around 5.2, 5.3. So it had to be connected to an sp3 hybridized carbon. I then looked in that 3 to 5 range, saw a 1H signal in that range. Probably then that's the CH attached to our oxygen. Now the CH is at the tail end of the oxygen region, which might mean that the oxygen is pulling, but then there's also another inductive effect for staying flexible. The CH is split into a quartet, meaning that there's 3 neighbors. And so I could attach a methyl group to get 3 neighbors. But that means I'd have to find a 3H doublet, and I do find that in my spectrum, validating its connectivity. And because it's just split into a quartet, that means I need to block splitting from this right side. And if I connected it to the benzene ring, I'm then connecting to a carbon with no hydrogens, ensuring that that CH proton is just split into a quartet. And that would also give it the chemical shift, being pretty far, honestly, at the tail end of that oxygen region. And then finally, the other signal to reconcile was a 3H singlet appearing in that 1.5 to 2.5 range. That would be our third substituent on the benzene ring. Okay. Moving on to example L. All right, starting with L here, we're going to do the IHD. Number of carbons times 2 plus 2 gives me 22. Minus the actual of 12. No nitrogens or halogens, forcing me to adjust that. That would come out to 10 over 2, which is 5. We're going to assume that means a benzene ring is present, plus another pi bond. Okay. Now that being said, I'm going to look in the aryl region of 6.5 to 8 to see how that benzene ring is substituted, and I see that 5H bond fire, implying that we have a mono-substituted benzene ring. Okay, so 1 substituent's coming off. I then keep in mind that I've got one other IHD, and I am seeing vinyl signaling in that 4.5 to 6.5. Some of those are a little bit close to 4, but that's okay, because I'm seeing, doublet of doublet, doublet of doublet, and 1 hydrogen integrations. So I'm not going to assume it's directly connected to the ring, rather I'll build that piece separately. I likely have an alkene pi bond, and there's 3 of those hydrogens off the alkene. Now, given that they're all doublet of doublets, what that means is that this alkene needs to connect to either carbon without hydrogens or oxygen atom. Okay. Then thinking about that oxygen atom, the oxygen would cause protons to shift in this 3 to 5 range. I've already reconciled that these are vinyl signals, so this one here could be impacted by the oxygen. What I'm going to do is build separately for now. I'm not going to assume connectivity to the alkene yet. Attached to that oxygen, I'd likely have the CH, which is split into a quartet. And for that CH to be a quartet, it would have to be attached to a methyl group. Okay, and then that methyl group would have to be split into a doublet, and I am seeing a 3H doublet. So very quickly, we see that we've reconciled all the signals. Now the CH here, that needs to connect to a carbon with no hydrogens. So what that means is I can't connect that directly to the alkene because, well, then that hydrogen there would be split, and then this would be a doublet of doublets. So it's likely the case that I need to connect that CH to my benzene ring. Okay, so I'm going to have my CH, which is attached to a CH3. Then we've got our oxygen. And then how we reconcile our carbon-carbon double bond is that the alkene could be directly attached to the oxygen atom. Okay, we said it could be connected to carbon directly or an oxygen without, or to an oxygen. Now, that being said, a further validation of that is we don't see any other signals in the oxygen region besides that one. So we need to connect to here a carbon atom. Okay. All right. Now, that being said, this would be our structure. Okay, kind of anticlimactic, this one. But that being said, notice how the oxygen is attached to the alkene directly. It could resonate in, and that resonance donation would cause shielding. That's likely why we're seeing some of those vinyl hydrogens appearing more upfield. Now, to recap this quickly, we said there's 5 IHD, likely implying a benzene ring and 1 pi bond. We looked at the benzene region first, our L region of 6.5 to 8, and we saw the 5H bond fire indicating a mono-substituted ring, so benzene ring with 1 substituent. I then looked at my vinyl region of 4.5 to 6.5, and I saw signaling in that region. I'm going to make the assumption that these 3 signals here are my vinyl protons. Okay, this one doesn't scream vinyl necessarily, right? So I said that there's an alkene pi bond with 3 hydrogens. I then saw that each of those hydrogens were just doublets of doublets, which means that I can't connect to a carbon here with hydrogens. So it has to be either a carbon with no hydrogens or the oxygen, but we didn't make that assumption yet. I then thought about my proton on a carbon bonded to oxygen region of 3 to 5. There was 1 signal in that region, a 1H quartet. So I'd have a CH bonded to a CH3, further validated by seeing that 3H doublet. And that CH is appearing kind of at the tail end of that 3 to 5 region, which likely means that it's having another inductive effect, potentially one of our pi systems. When we thought about that being the alkene, it couldn't be the alkene because then the splitting wouldn't work out for that hydrogen or for this hydrogen. So that validated that here we had to connect the CH to the benzene ring, which is what I did. Then on the other side of that oxygen, we need a point of connectivity, which could be this other piece that we have yet to reconcile, which is the alkene. Putting that all together, we have our benzene ring attached to the CH, which has the methyl group and the oxygen attachment. And then we can directly attach the oxygen to the alkene pi bond, which would ensure that all those hydrogens are just doublets of doublets. All right, moving on to the last H1 NMR example, example M. So starting with our IHD, number of carbons times 2 plus 2 would give me 20, 9 times 2 plus 2. Minus the actual of 18, no nitrogens or halogens, forcing me to adjust that, over 2. That comes out to be 2 over 2, which is 1 IHD. Now, right away, as I'm looking at the most downfield shifting signals, I see that it's in my vinyl range, 4.5 to 6.5, likely indicating that the 1 IHD represents a carbon-carbon pi bond. So I'll start by drawing a carbon-carbon pi bond, and I'm seeing specifically 3 vinyl signals. So 1, 2, and 3. Remember, if one of those hydrogens is more complex than just a doublet of doublets, that would be the hydrogen close to the substitution of that alkene. And for that to be a doublet of triplet, I'd have to connect to a CH2 carbon. Okay? So we've reconciled our vinyl signals, and we've said that there's a CH2 adjacent to the alkene based upon that 1 hydrogen here being a doublet of triplets. Now, keeping in mind that I've yet to use my oxygen, but I've satisfied my 1 IHD with my alkene pi bond. Then I'm going to look at my other 2H signals here, figuring out which one that is. And because they're both doublets, it doesn't really matter which one I choose. I'm going to probably assume it's the more downfield one. I'm also going to acknowledge that that 2H doublet signal, both of them for that matter, are in this region of proton on a carbon bonded to oxygen, which is 3 to 5. That would be a validation to connect the oxygen to the CH2. And the oxygen connecting to that CH2 and it connecting then to the pi system would probably give a more downfield shift to that CH2 compared to the other one, because we have the 2 inductive effects there. Now, that being said, building on the other side of the oxygen, I'd likely have the CH2 here. Okay, so on the other side, I've got a CH2, and that's also split into a doublet, which means that it has to connect to a carbon with 1 hydrogen. And so I scan my spectrum for a 1H integration, and I see a 1H integration here. Now, it's a little bit tough to tell if that's a septet or not, right? Now, if there was, say, 2 methyl groups coming off, then I'd have to see a 6H doublet. And I'm seeing a 6 hydrogen, but I'm noting that it's a 6 hydrogen triplet. And then I'm seeing another 4 hydrogen signal that's fairly complex. So what I'm going to do here is some problem solving. Because to get 6 hydrogens that are equivalent, I would have to have 2 methyl groups that are each attached to a CH2, but ultimately those CH2s need to connect to a point of commonality. They need to share a point of connectivity for those methyl groups to be equivalent. But that would kind of check out because we also need to have a 4H integration, which would indicate 2 equivalent CH2s. And we could then maybe connect that to this CH. In other words, our CH could connect to two CH2 groups, which would be equivalent. That would be our 4 hydrogen signal. And then it'd have methyl groups coming off each of those CH2 groups, which would then give us our 6 hydrogens that are equivalent, split into a triplet by the adjacent CH2 group. So here's what the structure would look like skeletally. You have our alkene, a CH2, your oxygen, then a CH2, which is then bonded to a CH, and then has 2 ethyl groups off that CH. Okay, so a little tricky. Let's recap that. We calculated the IHT that was 1, and right away, looking at our most downfield shifting signals, we saw the vinyl region light up. That means that our 1 IHT is a carbon-carbon pi bond. I saw 3 hydrogens in that vinyl region, so I made an alkene pi bond, put on 3 hydrogens, and one of them was a doublet of triplets, implying that we have the alkene substituted by CH2 to make this one into a doublet of triplets. I then went looking for that signal, and there's 2 CH2 doublets, and given that it's in the oxygen region as well, that means that the CH2 is likely connected to the oxygen, and the CH2 wedged in between the oxygen and the alkene is likely the more downfield shifting CH2 experiencing 2 inductive effects. Then building on the other side of the oxygen, I saw a CH2 signal here, which was a doublet, implying that I have a CH2 on my oxygen, which is then adjacent to a carbon with 1 hydrogen. I then found that carbon with 1 hydrogen. And it was a little bit tough to tell based upon the splitting what we'd attach to. But we knew it couldn't just be, CH bonded to 2 methyl groups, because I would have then needed to see a 6H doublet, but my 6 hydrogen signal present was a triplet. So from there, I needed to do a little bit of problem solving. I had to say, well, to get 6 hydrogens that are equivalent, they would need to have a point of commonality in their connectivity. And also, for them to be a triplet, they would have to each be adjacent to a CH2. And then those CH2s would have to connect to a point of connectivity that was similar for them to be equivalent in giving us a 4H integration. And so ultimately, we could connect them to that CH. So a little bit tricky to explain that, but hopefully that clicks, right? We had to have a CH adjacent to CH2s, giving us 4 hydrogens, and we had our 2 methyl groups that were equivalent, but that would be a 6H triplet. So sometimes it's a little bit tricky, in other words, to use the splitting pattern to fully determine if it's like a sextet, quintet, and so forth. If you run into that, do some problem solving to figure out how you'd have to arrange that to just get the integration values to match up. That's more or less what I did there, match the integration and splitting to finalize that chain. All right, so that completes our discussion of H1 NMR spectroscopy. The next part of this video series will be about aromaticity, starting on page 29. H1 NMR is so important. The last thing I'll leave you with is, you have to be really, really fluent with H1 NMR. It's also very easy to make mistakes. So please, please, please take whatever time is necessary to get splitting down, to get chemical shift down, integration, number of signals, because ultimately we put that all together as we determine the structure of our compound, doing spectral elucidation. We always start with our IHD. We read downfield to upfield. We get an anchor point and build from there. If you have a nitrogen and an oxygen and a broad singlet in that 2 to 7 range, we had to determine OH versus NH via problem solving. We can't assume with a chemical shift exactly what it would be. Okay. And with 1 IHD, we assume 1 pi bond as opposed to 1 ring. If that doesn't work out, we can always go back to it being a ring. And whenever we have our alkene pi bonds present, given vinyl signaling, we draw on the appropriate number of hydrogens. And if one of them is more complex than just a doublet of doublet, that means that off the alkene, there's some type of alkyl group that's also causing splitting of the 1 hydrogen closest to that substituent. If all of them are just doublet of doublets in the vinyl region, that means we either have to connect to a carbon with no hydrogens or to some lone pair atom. And whenever you have a benzene ring present, we determine that with IHD. You look at the benzene region to figure out if you have ortho, meta, para, or if it's monosubstituted. And if you see none of those patterns, it's not ortho, it's not meta, it's not para, it's not monosubstituted, then you likely have some type of tri-substitution pattern, and you figure out how to arrange those to align with the number of signals in the splitting in the aryl region. So take time, practice this, go back and watch the video if necessary, but practice, H1 NMR structure elucidation. And for those of you who use Rogue Chem, on the Rogue Chem drive to show you this, in the H1 NMR folder, you have a bunch of practice. We have structure elucidation set 1 through 16 and structure elucidation set 16 through 35, right? So with that, we're going to transition over to aromaticity in the next video.